In this video, we're going to look at an infinite geometric progression, or an infinite GP. Here in this example, we have got a geometric progression. The first term is 18, and the next term is 1.8, the next term is 0.18 and 0.018, and so on. So here, if we just write down what we have, we've got your A is equal to 18, and your R, how you get from one term to the next, you go from here to here by multiplying by 0.1. So we'll see that in a wee bit. Okay, so your first term, sum of the first term is just going to be 18. Sum of the first two terms is going to be 18 plus 1.8, so 19.8. Next three terms is going to be 19.98. The four terms, is 19.998. The sum of five terms is 19.9998, and so on. So it's pretty clear to see what's happening in this one. Every term you go along gets smaller. So you're adding on a smaller amount, and eventually, after a while, basically you're going to be adding on such a small amount that it does not make a difference. So there will be a limit to the sum of this thing. So you can see here 19.8, 19.98, 19.998, 19.9998. You can see it's very quickly going to a limit, and clearly the sum of Sn is approaching the value 20. So we say that the sum Sn tends towards a limiting value of 20. So if we went to the infinite term, your sum would be equal to 20, and that's it. Okay, if we look just down here at what our formula for the sum of the n terms was, it was Sn is equal to A upon 1 minus r to the power of n over 1 minus r. So this sequence is said to converge when r is between -1 and 1. So it's a bit like your binomial distribution, binomial expansion. It converged if modulus of x was less than 1. So here your r is less than 1, and if your r is between -1 and 1, then each term gets smaller and smaller. If r was not, say we started with r as being 10, your first term would have been 18. Next term would have been 180, and next term would be 1,800, and so on. So it's not going to converge to finite limit because it's getting bigger and bigger and bigger. So it's going to go to infinity, this particular one. Okay, so your r has to be between -1 and 1, or better way of saying that, remember, is that your modulus of r has to be less than 1. So if that is the case, what happens to this term? If you ever put in a number less than 1 on your calculator, so say you put in just 0.1 or 0.5, and you even just do like 0.5 to the power of 100, on your calculator will come out as an incredibly small number. So basically, if r is less than 1, this value tends to 0. So as your n tends to infinity, then your r to the power of n tends to 0. So really, we'll just write that down as n tends to infinity, r to the power of n tends to 0. So that's why this term here can be replaced with 0. So the way we say this then, so basically, therefore your sum of your n terms goes to a over 1 minus r as n tends to infinity, or the nicer way of saying it is the sum to the infinity is equal to a over 1 minus r. And again, you must learn this formula. Next part says, use this formula for the above GP to find its sum to infinity. So this is what we talked about. We know the answer is 20, or we assume the answer is 20. We're going to now prove that using the sum to infinity formula. So I've just written down what that GP was. It was 18 plus 1.8 plus 0.18. So again, we'll just write down here your A is clearly the first term is equal to 18. Your R is equal to 0.1. And your formula for your sum to infinity is a over 1 minus r. So in this case, that's going to be 18 over 1 minus 0.1. I will just go on here and finish this off. So that sum to infinity is equal to 18 over 0.9. Of course, it's a calculator exam. You can do that in your calculator, but there's no difficulty here anyway. So we'll just multiply top and bottom to get rid of the decimal in the bottom line. Multiply top and bottom by 10 to give you 180 over 9, which is 20. Done. So we have shown when your A was 18, your R is equal to 0.1, your sum infinity is a over 1 minus r, so 18 over 1 minus 0.1, which becomes 18 over 0.9, multiply top and bottom by 10 to give you 180 over 9, which is just 20. So again, just a wee reminder then, that's very important, your sum infinity for a GP only exists whenever a modulus of r is less than 1. And the terms of the series will decrease in magnitude, and this means that the series is convergent. Another infinite series example here. So we've got 16, 12, 9, and so on. So your a is clearly equal to 16. Your r, it says way back in your notes, to get your r, you can just do the term divided by its previous term. So we'll just do 12 divided by 16. So I'll just tidy that up. R is equal to top and bottom divided by 4, so it's going to be 3 over 4. Okay, so first of all, modulus of r is less than 1. Therefore, the sum to infinity exists. So we'll just write that in, and then we'll just get cracking. So your sum to infinity is a over 1 minus r. So in this case, that's going to be 16 over 1 minus r, which is going to be 1 minus 3/4. And again, I'll just go over here and finish that off. So your sum to infinity is 16 over 1/4. And 16 divided by quarter is the same as 16 times 4. So it's going to be 64. And that's it. Okay. This example says express a recurring decimal 0.235, where the 35 is recurring, as a fraction of its lowest term by considering it as a GP. Okay, normally we would do this a very different way when we looked at it in GCSE mathematics, and that, to be honest, that method, the GCSE mathematics way, is probably the nicest way of doing it, but they've asked you to do it using GPs, so we have to do it this way. So it is 0.235, and the 35 is recurring. Let's just write out what that would look like. So that's going to be 0.235, 35, 35, dot, dot, dot. That's what that's going to be. And we're going to write that a different way. So we'll have to try and get this in GP form. We have to split it up into 2 bits. We've got the 0.2 and then the rest of the thing here as well. So I'm going to do 2 digits at a time. So the first 35 is 0.035, remember. The next 35 is 0.035. The next one is 0.5 zeros and then the 35. So 0.000035 and so on. Okay, if we go on with this then, if we look just at this bit, what you have, your a, your first term is 0.035, and your r, how you get from this one to this one, for example, you would multiply by 0.01. So it's 100 times smaller, so you multiply by 1.01. So what you've got then, overall, this is going to be, we're going to write the 0.2 as 1/5, and then this is my sum to infinity. So my sum to infinity, remember, is going to be a, which is 0.0035 over 1 minus my r, which is 0.01, and fire that all into your calculator. Well, I'll just fire in the second bit into my calculator. I'll just write the 1/5, so I've just put this bit here into my calculator, and it came up nicely in my calculator as 7 over 198. So my answer then, I'll just go across here, is going to just be 233 over 990. Okay, if you're unsure, if you don't think that's right, all you have to do is do 233 divided by 990 on your calculator, press SD, and you'll see what you get. You get this as your answer. We're going to look now at a couple of examples where we use APs and GPs in real life situations. This first example is an AP. So in this question it says, John is saving £1,190 to pay for a holiday over 20 weeks. He decides to save X pounds in the first week, and then will increase the amount he saves each week by Y pounds. Given that he saves £72 in the 13th week, find X and Y. Okay, first thing to do in a question, I guess, is write down what it is. So it's an AP. My first term is the amount he saves in the first week, it's X. My common difference, D, is what he increases that by, so he increases that by Y. and my n is 20 weeks. Now, the formulas we know for an AP, we have un is equal to a plus n minus 1 d. Sn is equal to n over 2 times 2a plus n minus 1 d. Okay, so we're good to go. We have everything we need. Now, the first thing it says that jumps out at me, it may jump out at you in a different order, that's fine. It says, given that he saves £72 in the 13th week, so that tells me U13, my 13th term, is equal to 72, which means 72 is equal to A plus 12D. But I really should have said that's x plus 12y. Okay, that's my equation 1. Apologies. And then my second thing I've spotted here is he saves the 1,190 over 20 weeks. So my sum of 20 is 1,190. So 1,190 is equal to 20 over 2 times my 2a, which is 2x, plus n minus 1, which is going to be 19 times my d. So that's it. And then we tidy that up. That's going to be 1190 is equal to 10 times 2x plus 19y. And you can divide across by the 10 and make life a wee bit easier. That's 119 is equal to just 2x plus 19y. And that's your equation 2. Okay, all we're going to do now is solve these two things. So just write down my two equations. I had 72 is equal to x plus 12y was my equation 1. 119 is equal to 2x plus 19y. That was my equation 2. So I'm going to multiply my first equation by 2 to give me 144 is equal to 2x plus 24y. And I just do the top one minus the bottom one. So I'm going to do what I'm doing here is equation 2 minus the 2 times equation 1. And 119 minus the 44 is going to be minus 25. 2x minus 2x is going to be 0. And 19 minus 24 is going to be minus 5y. So minus 25 divided by minus 5 is going to give me my y. My y works out to be 5. Sub that back into the first equation. I'll do that over here. So put that back into equation 1. You're going to have 72 is equal to x plus 12 times the 5. So 72 is equal to x plus 60. So 72 minus the 60 is equal to your x. So your x is equal to 12. Let's see, have we answered this question? Find x and y. We have done it. You can clearly see your answer for x is x equals 12. Your answer for y is 5. The second example says, Bill has borrowed a sum of money from a friend. He agrees to repay £200 at the end of the first month and will decrease his payment by 5% each month until the loan is repaid. By modelling the repayments as a series, determine how much he will repay at the end of the 12th month and calculate the amount of money paid off. Okay, first thing, this is a GP, as you've got a first term, which is 200, and each month his repayment is decreased by 5%. So to decrease something by 5%, you multiply it by 0.95. So that's what we have. And also, we'll write down a couple of things for the GP. Our UN for a GP is AR to the power of n minus 1. Your SN for a GP is going to be equal to A upon 1 minus R to the power of n all over 1 minus R. So I think that's everything we need. We can get cracking. It says how much will he repay at the end of the 12th month. So first thing we're looking for is U12. So U12 is just going to be equal to 200 times the 0.95, and the 0.95 is the power of n minus 1, so 12 minus 1, which is just going to be 11. And if you do that on your calculator, 200 times 0.95 to the power of 11, you will get £113.76, and that's the 2 decimal places. Okay, the next thing, the last thing that we need to do here is find our sum of our first 12 terms, because this is what he's paid over the whole year, the whole 12 months. So again, that was just A, which was 200, times your 1 minus 0.95, and that's now to the power of n, so that's now to the power of 12, and then that is being divided by 1 minus the 0.95, and again, you just do that on your calculator and see what you get. So my sum of the first 12 terms was equal to £1,838.56. Okay, you're now ready to sequence and series exercise 5, and sequence and series exercise 7 is a summary exercise of everything you've done.